Hello and welcome to Mclean 360. So in this video, I want to introduce you to logarithmic decrement. All right. Why are we calling it logarithmic decrement? All right. So what we have here is the response of an underdamped system over here, right? And how did I know this is actually an underdamped system? So we said that the response of our underdamped system is what? Some C E minus zeta omega nt sine omega dt plus phi, right? And this E minus zeta omega nt is the exponential function. So that is where you are getting your exponential curve from. And I have my sinusoidal function. And this sinusoidal function is the one that is giving me that kind of motion, right? Okay. So that is it. Now we want to say that, okay, if my response is this, then let's say the first amplitude. Okay, so this is the A1, the first amplitude. Let's say that the first amplitude is the response, and it can be written in the form, let's say C E minus zeta omega nt sine omega dt plus phi. Now looking at the second amplitude, then I can also write the second amplitude in the same manner, but this time around I'll do minus 2 zeta omega nt sine 2 omega dt plus phi. Why are we doing this? Now, what this means is that, the sinusoidal function is not changing shape. It is still sinusoidal. Exponential function is still exponential function. But what happens is that the values of the exponential function will be changing depending on the value of your amplitude, right? So what we will just be doing is just to place the amplitude in front of the, so if I want to get the second amplitude, I'll just put 2 here, and that is what I have here. And then, in fact, what this means is that I can go on and on and on to any other amplitude, and we say let R be, so we have what we call the R amplitude. So the first amplitude is R equals 1. Second amplitude is R equals 2. The third amplitude is R equals 3, and so on and so forth. Now, what happens is that if I'm saying that this is my Rth amplitude, then I can express the Rth amplitude as some C and then E minus minus R rather, minus R zeta omega nt sine R omega dt plus phi. And what this means is that what will be changing is what? Is only the amplitude, but the function remains the same. The amplitude only changes. Okay. And if that is the case, then this can also be said that sine omega dt plus phi is the same or equivalent to sine R omega dt plus phi. Why are we saying this? Because the function remains the same. The sinusoidal function remains the same throughout. It's only the amplitude which changes. And if this is true, so this is the assumption that we are making. If this is true, then I can say that, so let's say this is equation 1, and then this is equation 2. From my equation 1, I can say that A1 divided by C E minus zeta omega nt is the same as what? AR divided by what? CE minus R zeta omega nt, right? Okay, now if that is the case, then C will take off C, and let's write A1 divided by AR. So A1 divided by AR is going to be, that is, so A1 over AR is going to be E minus zeta omega nt divided by what? E minus R zeta omega nt. And in fact, this is the same as E minus zeta omega nt minus, right, minus r zeta omega nt. So we are just trying to play around our indices, isn't it? If I have e here raised to the power something, e here raised to the power something, then I can just substitute or bring this up and subtract. So if the indices are dividing, they are actually subtracting. If I do this, I'm going to get a1 over ar to be e minus zeta omega nt plus r zeta omega nt. And this will also be the same as e zeta omega nt into what? R minus 1. Is that right? So I've factorized out zeta omega nt, and I'm saying that r minus 1. Now, a careful study here. Okay, so, all right. A1 divided by AR is now what? E zeta omega nt r minus 1. A careful study over here will reveal that my so the t that we are talking about is actually the period. It's actually the period from our damped natural frequency. And in fact, you know, the damped natural frequency is omega n into 1 minus zeta squared. And don't forget that if I am interested in the damped natural frequency, the period associated with that, the period is going to be, so omega d is what? 2 pi divided by the period. The period. Is that not it? All right. So let me bring it here. This is what we are trying to say. We are saying that there is a t here, right? Omega nt. But we are saying that this t that is here is actually the same as the TP. And this TP is coming from the damped natural frequency. So the period will be given by 2 pi over omega d. That's what we are saying. So it's going to be 2 pi divided by omega n into 1 minus zeta squared. So that's what we are basically saying. And if that is the case, then I can substitute this so that I have a1 divided by ar as what? E zeta omega n multiplied by what? Omega n, multiplied by 2 pi divided by omega n 1 minus zeta squared, and then multiply by r minus 1. So the omega n will take off the omega n, and then I'm going to end up with what? a1 over ar as the exponential of zeta into what? So the exponential of 2 pi zeta r minus 1, all divided by what? 1 minus zeta squared. So this is actually an exponential. Okay. Exponential of all of this. Now, how can I get rid of the exponential? I need to take the natural log of both sides. So log e 1. So log e of a1 over ar is the same as log e. And then I'll do 2 pi zeta r minus 1 divided by the square root of 1 minus zeta squared. But in fact, log e is the same as the natural log, which is ln. So ln of a1 divided by ar must be equal to what? In fact, log e is what? 1 from our mathematics class, from our logarithm class. So I'll get 2 pi zeta r minus 1, all divided by what? 1 minus zeta squared. And in fact, we have gotten a very important formula here. And, you know, this formula is telling us that as I move from the first amplitude to the second amplitude, there is a decrement. And this decrement is actually a logarithmic profile. So what happens is that in practice, if we want to find the damping ratio, so for instance, If I am interested in finding the damping ratio or I want to find the damping coefficient, what I would do is that I will study the amplitude. So I will look at the first amplitude, which is A1, and then I will compare this A1 to any other amplitude. If I know the amplitude, if I know the first amplitude, and then I know about any other amplitude, this can help me to find the um, the damping ratio. Yeah, the damping ratio. So that is logarithmic decrement. And let me tell you this. Please, the R here that you see is the RF amplitude. Okay, there's the RF amplitude. And let me show you the secret. So let me show you the secret. And this is where most of the students get it wrong. You know, whenever you are analyzing systems like this, what happens is that let's move through one cycle. So let's say I am here, right? I go through a cycle and I finally land here, right? I go through another cycle and finally land here, isn't it? Now watch this. After one complete oscillation or cycle, you land at the second amplitude. After two cycles, so this is one cycle. You are at A2, and this is another cycle. You will be at where? At A3. So it means that as I move from amplitude to amplitude, it will be what? So the RF amplitude is n plus 1. That's all. So if I have 4 cycles, I'll be at the 5th amplitude. If I have 3 cycles, I'll be at the 4th amplitude, right? And look at this. In fact, after one cycle, which is n equals 1, R is what? 2. I am at the 2nd amplitude. So R is what? N plus 1. So the amplitude is equal to the number of cycles plus 1. That's what we are saying. So R amplitude is equal to the number of cycles. So n number of cycles plus 1. And that is how we are going to solve for this. And sometimes they can tell you that the after 4 complete oscillations, or maybe after 5 complete oscillations, the amplitude reduces to maybe 1/4 of the original value. So it means that 1/4 of the original value. Sometimes they can tell you that 10% of the original value. So this is 10% of the original value. Then you just make sure that you should be able to solve this. So if I say that the new amplitude is maybe 1/4 the original, then in that case, maybe if I say after 2 cycles, so after 2 cycles, the vibration amplitude reduces to 1/4 of the original value. Then it means that after 2 cycles, R will be what? 2 plus 1, which is 3. So after 2 cycles, I'll be at the 3rd amplitude. Therefore, A3 is what? 1/4 A1. And so if I want A1 over A3, then we are saying that this is going to be what? 4. And so you are going to do the length of what? 4 over here. And then you will place R by 3 inside the equation. And then you can solve for the damping ratio. Okay. So that is the logarithmic decrement all about. Thank you very much for watching the video.